This is a video on differentiability, and differentiability talks about a few basic things. It talks about, first of all, where a function is and is not differentiable, which means where we can and cannot take the derivative. And differentiability is a little bit tied to continuity, and we'll talk about that also. So that's there too. Let's go ahead and start with our definition for differentiable. A function f is differentiable at a point x equals c if. And now we have a few things to talk about. First of all, if f is differentiable, f must be continuous. So f must be continuous at x equals c. And let's go ahead and remind ourselves what continuous at a point meant and what we had to have for that. The first one was we needed a point. So we had to have a point where f of c equals some number L. And the second thing was that the limit as x approaches c from the left of f of x had to equal the limit as x approached c from the right of f of x, and those limits were both equal to L, and noticed how those matched up. So if f is different, so a function is differentiable if, first off, f has to be continuous at c. The second condition is that not only must the values of the function be the same at x equals c, but this other condition, where the limit as x approaches c from the left of f prime of x must be equal to the limit as x approaches c from the positive side of f prime of x. And these both have to be the same value. I'm going to call it k. And k has to be a number. And by that I mean not infinity. So it's got to be the same thing, and it has to be a number or not infinity. Let's go ahead and break that down a little bit conceptually as to what that means. The first part of that definition was the limit as x approaches c from the left of f prime. And really, I say derivative, you think slope. This is the slope of the function from the left. Slope from the left. And the rest of that definition was that the slope from the left had to equal the limit as x approached c from the plus side of f prime of x. And this right-hand side, well, that's f prime again, and f prime is the derivative. I say derivative, you think slope. This is the slope from the right. And all that differentiable means is that the slope from the left equals the slope from the right, and this is a number. So, yeah. Another way to put this is that because the two slopes are equal, let's say here's c, and let's say that this is my function coming in from the left like that. And so there's that slope right there in blue, kind of that tangent slope. And then the slope from the right has to match that. It has to match that in green. And so the function can go wherever off it can, but we have to make sure that the tangent line at C is equal to the blue line, so that the green and blue slopes are equal. And if I get rid of the green and blue lines, you can see something very nice about the function in black at C. Check it out. The function is very smooth at C. There's no jumping around or anything like that. So another way we can say differentiable, f is differentiable, means that f is smooth. And we talked about that on that first day also. Here's some graphical examples of functions that are differentiable. Really, any polynomial that you draw will be differentiable because, you know, it's continuous. You can draw it without lifting up your pen or pencil, and it's smooth, right? You don't have to do any sharp turns or anything like that. So things that are always differentiable are polynomials. And then sine and cosine are both differentiable everywhere because they're nice and smooth and not bumpy at all. Notice that tangent is not differentiable because tangent has those vertical asymptotes there, and because tangent is not continuous there, it's also not differentiable there. A very good example of a function that is continuous but is not differentiable is absolute value of x. Check it out. Is this continuous? Yes, because I drew that without lifting up my pen or pencil. But here, notice that the derivative from the left, so think about it, the slope here, not the y values, the actual slope, that slope is -1, And the slope from the right, that slope there, that slope is positive 1, and those two are not equal to each other. So here we can say that absolute value of x is not differentiable at x equals 0, just like that. Another example of where a continuous function might not be differentiable is at a vertical tangent line. So here's a function, y equals the cube root of x, and that function looks like this. And now if you look at that, at what's going on at 0, I didn't draw it exactly right, but if you, at 0, basically this function comes in and that slope there is about a straight line. You can graph that and verify that yourself, but remember with the definition of differentiability, those two limits from the left and the right of f prime, they had to be the same, and that number had to be a real number, not infinite. So a vertical tangent line has an infinite slope, but that's not good with our definition of differentiability. So here, the cube root of x is not differentiable. I'm going to abbreviate that as diff at x equals 0. Okay, not differentiable if you have a vertical tangent line or a place where you have a sharp turn like absolute value of x. The last thing is that there is a very deep connection between if a function is differentiable and if a function is continuous at a given point. And here are the main relationships that you need to know. The first one is that if f is not continuous, so if there's a jump or a gap or a vertical asymptote or a hole at a given point, then f cannot be differentiable at that point, because in order to be differentiable, f must be continuous at that point. So that's a pretty logical statement. Notice that it does not go the other way. We can't say that if f is not differentiable, then f is not continuous, because there are many examples where you can have a continuous function that is not differentiable, such as absolute value of x. Continuous, yes. Differentiable, no, at x equals 0. So you have to watch out for that. But if you know that the function is not continuous at a point, then it's also not going to be differentiable. If we switch the statement up a little bit and take what's called the contrapositive, here's what you get. You get that if f is differentiable, then f is also continuous. And that's because if f is differentiable, then you know that it has to be continuous, because that's one of the that's part of the definition for differentiability, is that if f is differentiable, f is also continuous. So again, notice that it does not go the other way. You can't say if f is continuous, then f is differentiable, because, bam, you have an example where you have a function that is continuous but not differentiable. So differentiability will stay with us for a while. It is a topic that shows up on the AP test, and it's good to just know, because, hey, differentiable math is smooth.